In the last lesson, we learned a little bit about deep time. These are very long periods of time that are hard to understand. And we learned that these are lengths of time that would be required for an organism like Glyptodon to change into the modern armadillo, as Darwin argued. Well, how old are these fossils that we find in the rocks? Here we have a set of rock layers here, and we've got two rows of fossils here, some trilobites down here and some kind of shellfish up here. Well, to find the dates, how old these fossils are, what modern scientists do is they typically find the dates of rock layers above and below the fossil of interest. And often they use volcanic ash, so deposits of volcanic ash. And we'll see that scientists can use modern methods to find the age of these ash layers, which then sets a boundary, a limit for how old the intervening layer might be. To understand this, we first have to understand what are rocks. Well, a rock like granite is composed of several different kinds of minerals bonded together there. Quartzite is made of one kind of mineral. Well, what are minerals? Well, again, here's granite. A rock is made of minerals like quartz, feldspar, biotite, and minerals are composed of elements. Now, these elements, these are the 92 different kinds of substances that make up material stuff in our universe, things like silicon and oxygen. And these 92 elements, you find them listed in the periodic table of the elements that you find in a chemistry classroom. But elements then have different properties, and the smallest unit of an element that has those properties is an atom. So let's imagine we have a chunk of granite here. Many rocks have trace amounts of uranium atoms in it. So uranium is one of the 92 different kinds of elements, and the smallest unit of the element is the atom. Now, something interesting happens to uranium atoms, though. They decay over time. They break apart. And when the uranium atoms break apart, it's called radioactive decay, they actually transform into a different atom of a different element. They turn into lead. Pb is the designation for lead. So uranium atoms are unstable, and they undergo radioactive decay where they transform into lead atoms. Now, what is radioactive decay? Well, we will be learning that atoms, there's a nucleus of the atom where you have protons and neutrons, and then surrounding the nucleus are electrons. Well, radioactive decay involves the nucleus of the atom. And in fact, the atom loses some of its the nucleus loses some of its particles, loses a couple of protons and a couple of neutrons. And then the resulting nucleus is called the daughter nucleus. But because it has a different number of protons, it's a different atom. So radioactive decay involves the loss of protons and neutrons from the nucleus. But when the number of protons changes, the identity of the atom changes as well. In fact, uranium goes through a series of decay events ending up as lead. Now, the decay of uranium atoms into lead, that's the key to how scientists are going to be able to date rocks, to get the age of rocks. Let's see how that works. In this illustration, we see three rocks, but it's not really three. It's the same rock at three different times. So we have the newly formed rock and the rock sometime later and even later. Now, the red dots here are uranium atoms. So again, many rocks have trace amounts of uranium atoms. And you'll notice in the rock in the middle here, some of the red uranium atoms have transformed into lead. They've undergone radioactive decay. So for example, this particular uranium atom decayed to become lead. But the next door neighbor uranium atom did not. It remains uranium. Now, scientists cannot predict when an individual uranium atom will decay, but they can measure the rate of decay. So how long do you have to wait until one of them decays, and then two of them, and three, and so on? And then you can get an idea of how long it takes for a population of uranium atoms to go through this radioactive decay process. So for this middle rock here, we appear to have a situation where there are roughly equal numbers of uranium atoms and lead atoms. So about half of the original uranium atoms have decayed into lead. The amount of time that takes is called the half-life for uranium. In fact, scientists then have measured the rate of decay, and they assign uranium's half-life to 704 million years. And that's how long it takes for about half of the uranium atoms to decay into lead. Now, no scientist has been around for 704 million years, but remember, they're measuring the rate of decay. And so they can mathematically then sort of extrapolate to get the half-life. Now, rocks that are older than 704 million years are going to have relatively more lead because the remaining uranium atoms are going to undergo radioactive decay into lead. So rocks that are enriched in lead relative to uranium are older than the rocks that have equal amounts. We can see this relationship on a graph like this. So the y-axis is the percent of each material, and the x-axis is time in millions of years. So 1,000 million would be 1 billion years. You'll notice uranium is in green and lead is in gray. If we start with a lump of uranium, pure uranium, over time those atoms will begin to undergo radioactive decay and turn into lead. So as the uranium decays, the lead increases here, right? And where the lines cross, this is the half-life of uranium. So the percent of each material, so 50-50, so 50% of the material is lead and 50% uranium. And for uranium, that's 704 million years. As the lump of uranium gets older and older, more uranium atoms will decay, and so lead will accumulate in a corresponding fashion. So this then is how scientists can measure the age of rocks. If they can measure the relative quantities, relative amounts of lead and uranium in the rock, they can estimate how long that rock has been around since its initial formation. So again, back to our picture then, if we want to know how old these fossil shellfish are, or the trilobites, we want to measure the age of the volcanic ash above and below the fossil of interest. Volcanic ash indeed has uranium in it. So we can imagine these little chunks here would be chunks of volcanic ash. And so this would be newly formed volcanic ash that will undergo radioactive decay. But why does the newly formed rock only have uranium and no lead atoms? Because after all, we're measuring the relative amounts of the uranium and lead to get the age. So for this to work, the original rock has to have no lead atoms in it, just uranium. Well, we have to then take a look at how these volcanic rocks are formed. So rocks are formed from the magma. And as the magma is cooling, there are different kinds of crystals in the magma. And when the rock cools, the crystals are embedded in the newly formed rock or the ash that's ejected from a volcano. Now here's the key. One of the crystals in volcanic ash is called a zircon crystal. And we see a picture of the tiny crystal here. And here is the atomic structure of the zircon crystal. So it's got oxygen atoms and zirconium atoms and silicon atoms that are all kind of linked and bonded together in this fashion here. So this is what a crystal of zircon is composed of. 3 different kinds of elements, 3 atoms of 3 different elements. Now, the zircon crystals form in the magma prior to a volcanic eruption. Uranium atoms and zirconium atoms have a similar atomic structure. They have a similar arrangement of electrons, for example. And as a result, uranium atoms sometimes replace the zirconium atoms in the zircon crystal. So wherever you see a zirconium atom here, the gray ones here, sometimes a uranium atom can replace a zirconium atom and take up position in this kind of lattice work of atoms bonded together. Importantly, lead atoms have a different atomic structure, one which does not allow them to be incorporated into the crystal. So you're just not going to have lead atoms in the newly forming zircon crystals, but you can have uranium atoms. Thus, the zircon crystals have trace amounts of uranium but no lead atoms. And so this is time 0 for the radioactive clock. So the reason there are no lead atoms in the original crystals in the volcanic ash is because the lead atoms just cannot take up positions in the crystals. So that means these zircon crystals have uranium atoms and no lead atoms. And that then is going to allow scientists to simply measure the amounts of lead in the rock to get a sense of how long that rock has been around since its original formation. So as the uranium atoms decay, lead atoms accumulate in the zircon crystals. So finding the zircon crystals in a volcanic ash layer allows scientists to date the layer by measuring how much lead is present. The measured lead is inferred to be the result of radioactive decay of uranium. So since there was no lead in the beginning, any lead that's present must have been the result of radioactive decay from the uranium. And so then what we have is an ability to date the volcanic ash layers. And so if this layer is 495 million years and this layer is 510 million years old, then the shellfish have an age somewhere between those two dates. So it's amazing, though, then to think next time we see a volcano, we can enjoy its splendor and its beauty. This is the crater, the Haleakala crater on the island of Maui. But in addition now, with a little education, we can think about a picture like this and see all this volcanic ash, and in that ash are zircon crystals, and these volcanoes are ejecting tiny little atomic clocks. The zircon crystals forming from the magma here are going to have some trace amounts of uranium, and then that uranium is going to begin to decay into lead, and so the volcanoes are ejecting little atomic clocks. And this fact allows scientists to reconstruct the Earth's past. By using the radioactivity techniques to measure the age of rocks, scientists then can get an estimate of how old the Earth is. Some of the oldest rocks ever detected, some found in Canada, are 4.28 billion years old. Here we see a meteor crater in Arizona, and nearby that crater were small meteorites. They were dated to about 4.55 billion years. Now here we see our solar system, and here's Earth, and there's our moon. Well, scientists have retrieved moon rocks and dated them to about 4.51 billion years old. So lots of these measurements are then suggesting that the solar system itself is around this age. In fact, there are still lots of asteroids and comets and meteors still sort of in our solar system, and scientists think of them as sort of the residual material out of which the solar system was composed. In fact, NASA is sending a mission to one of these asteroids, Bennu, and that mission will return a sample of this asteroid back to Earth in 2023, and so we'll have an opportunity to measure the date of this, measure the age of this asteroid. The existence of radioactivity then allows geologists to give us a time scale for our story. Our story is a 4.5 billion year story from the origins of the solar system and our Earth until the Earth today. And in biology then, something amazing happened. A lifeless rock turned into a rock with life, teeming with millions of different species. We will tell that part of the story in the remainder of the course. But as humans trying to understand our place in the universe, it is very fortunate that there are some atoms in our universe that are unstable. Uranium atoms decay into lead. And if we can measure the relative quantities here, we can measure vast stretches of time. And this then has allowed us to determine that our home, our Earth, is about 4.5 billion years old. Of course, this is a really long period of time, really hard to understand intuitively, but nevertheless, this is the picture that modern science paints.